Bismillahir Rahmanir Rahim. Assalamu alaikum, dear students. Let's keep going with the previous lecture and push it forward in the present one. We discussed the historical evolution of special theory of relativity and the main contributors that made a tremendous contribution towards physics and particularly STR. So as far as postulates of STR are concerned, they are broadly divided into two sections. The first section can be titled as invariance of physical laws. It means invariance means that the laws don't change ever as far as the inertial frames are concerned. So let's state it, the laws of physics can be expressed in the same set of equations in all inertial frames of reference. You need to understand the very depth meaning of this postulate. This means that if two or more than two observers observe similar event from different inertial frames of reference, and they want to apply an equation, okay, any equation in physics, any you can say any law in mathematical form, so the equation will be equally valid in all frames relative to all of the observers. But the thing is, there will be a discrepancy between their observations. The outcome, the result of their observations will be different, but the equation that they are using in various inertial frames will be equally valid. So this statement means like that. Hopefully you have got that. As far as the second postulate is concerned, it can be entitled as the universal constancy of the luminal speed, meaning that speed of light is constant in vacuum. Okay, so the proper statement for that will be the speed of light in vacuum is the same for all of the observers, regardless their state of rest or of uniform motion. We can consider a receiver and a source of light, which may be a torch or anything else. In the first case, you can consider both the source and the receiver are stationary, okay, and the receiver is capable of measuring the speed of light. So in this case, even according to the common sense, the speed of light measured by the receiver will be c. In the second case, if both the receiver, the emitter, and the observer, okay, they recede one another, they move away from each other with a velocity, say v, then classical mechanics and the common sense say that the velocity of light measured by the receiver will be c minus v. But this is not the case in here, okay. The experimental fact is the velocity of light will be c again in this case. And in the third case, if both the receiver and the observer approach one another with a velocity v, then according to classical mechanics, according to intuition, the velocity of light measured will be c plus v. But again, it doesn't affect, this velocity doesn't affect the velocity of light, and the measurement made will be c. So it means that this velocity is independent of the state of rest or of uniform motion of the observer and the source. So these two postulates actually form a strong basis of special theory of relativity. And the velocity of light and its constancy uh, is uh, is quite important and of pivotal importance, I will say. And this is the root cause of relativity of space and dilation of time and relativistic increase in mass. So it means that nature has set an upper limit of speed, which is c in front of us, and we are unable to exceed this c or even reach c. We are unable to do that. So these are the immediate conclusions that can be drawn in here in the light of these two postulates. Relativity of space means that length is a one-dimensional space, right? Plane is a two-dimensional space, and volume is a three-dimensional space. As far as the measurements of various observers from inertial frames of reference are concerned, then the measurements made by these observers will be different from one another depending upon their relative velocity. If the relative velocity is relativistic, and the more it is, the more shrinkage they will observe in the space, whether it's length of rod, whether it's area of plane, whether it's a volume. So an observer relative to an area or a length or a volume is moving with some relative velocity will observe a strong shrinkage, and this shrinkage will increase as a function of increase in relative velocity. So we will discuss it in detail in the coming slides. As far as the time dilation is concerned, so time dilation is basically, dilation means extension, or in Urdu we can say that phailao. And the physical significance of this dilation means that the speed of time will decrease. Okay. So the clocks will tick slowly as relativistic velocity between the two observers increases. And remember, this time is affected by two factors very much. One is special theory of relativity, and the other one in general theory of relativity. In special theory of relativity, this is the relativistic speed or relativistic velocity that affects time, that dilates time, as a function of increase. And in general theory of relativity, this is a gravitational force that dilates time. But now we will discuss only the effect of relative velocity upon dilation of time. And the third consequence is relativistic increase in mass. As far as the mass is concerned, as discussed in previous slides, mass can be inertial and it can be material. So in here we will discuss only inertial mass. So this is a relativity of space. Suppose that this L0 is the one measured by an observer who is inside a frame of reference which is moving with a velocity v. Did you get it? Let me repeat. This L0, which is the difference of the coordinates of the two ends of anything like rod. So this L0 is the distance or length measured by an observer within the moving frame. Suppose we are ground-based observer, and another observer is inside the moving frame, and he made some observations of the length of a rod. So this observation is coming from the observer who is inside that frame of reference. This L is the length measured from a ground-based observer like us. We are watching the rod and the frame of reference moving with some relative velocity v, and the coordinates relative to us are x2 minus x1. So we have a Lorentz transformation equation that's discussed in the previous lecture. So L0 is x2 primed minus x1 primed, and x2 primed is related to x2 with the help of v and t2. So we have that equation. And similarly for x1 primed, we have the equation is basically x1 minus vt1. So making these substitutions, this equation reads like that. And we have introduced a gamma factor as well, which is 1 over 1 minus v squared by c squared under the root. So the two measurements were made in the fixed frame. This statement means that since the two measurements were made in the fixed frame, okay, so T1 and T2 are the same. So like the one written in here, T1 is equal to T2 because the two measurements were made in the fixed frame, in the same frame. So these two terms, this Vt1 and this Vt2, will be cancelled out mutually with each other, and we are left with L0 is x2 primed minus x1 primed, and this is reshaped as x2 minus x1 over 1 minus v squared by c squared under the root. And as you know, 1 over 1 minus v squared by c squared under the root is gamma, and this x2 minus x1 is L as written in here. So this L0 is equal to L gamma, and L is equal to L0 over gamma. So this is called length contraction. So the presence of this gamma is very important. It tells you that the more V you have, the more value of gamma will come out, and which will affect this L0 in terms of this L, and this L is actually the one measured by a ground-based observer, right? So this amber color, let's see in the next slide what this amber color means. This means that according to special theory of relativity, objects appear to contract in the direction they are traveling. This factor must be taken into account, that this shrinkage, this decrease, this shrinkage basically takes place in the direction an object is moving. Like we can consider this phase of Einstein moving rightward with some velocity. In the first instance, we don't have any velocity in here, so the picture, the phase of Einstein is normal. So as we see that this picture starts moving with 60% of the velocity of light, we can observe some sort of shrinkage in the picture, and once this velocity goes up to 80% of the velocity of light, this shrinkage becomes more apparent, and with 99% of the velocity of light, the shrinkage becomes much clear, and then we are not even in position to recognize the face. So hopefully you have got the very notion of this length contraction, or even relativity of space. So this is in terms of area, and as far as one side of this rectangle is concerned, then this is in terms of length. So the second consequence is time dilation, and I think it's more or less the same compared to the length contraction. This T naught is the time interval measured in the moving frame, measured within the moving frame by an observer who is inside that moving frame. And this time interval basically is the one measured by a ground-based observer relative to which that frame of reference is moving with velocity v. And thus we can figure it out with the help of Lorentz transformation equation, the one discussed in the previous slide. So this T is T2 minus T1, and this T2 can be linked with T2 primed, V and X2 primed, and C in this shape, right? This is T2 prime plus Vx2 prime over C square. And similarly, T1 is T1 primed minus Vx1 primed over C square over 1 minus V square by C square under the root. And again, the locations are the same. Okay, that's x1 and x2 are the same as written in here. Since the time measurements in the moving frame are made at the same location, okay, so that's why x1 primed and x2 primed are the same. So when they are the same, then these two terms can be cancelled out mutually with each other, and we are left with T is T naught over 1 minus V square by C square under the root, and T is equal to T naught gamma. So again, you know, when that gamma appeared in the denominator in the previous equation, then it caused contraction decrease in the length. But in here, this is directly multiplied with this T naught, so it means that this increases this ratio, this factor. So it means that this T compared to T naught will go up. Hopefully you got that. Let me repeat it. This T is the time interval measured by a ground-based observer like us. We are watching an event from outside, and this T naught is the time which is the proper time, and that's measured by an observer who is inside the moving frame of reference. So this is the proper time, right? And this is the dilated time. So the more gamma is, the more will be this dilated time. And the gamma increases as a function of increase in the relative velocity. So what we can say as far as the notion of space, time, and space-time is concerned, Einstein discovered that there is no absolute time. In addition, it depends upon the state of motion of the observer. As far as Newton's school of thought is concerned, then we can say that space is a separate entity, a separate agent, a separate factor, and time is another factor that are quite independent of each other, and they are separate factors. As far as Einstein idea is concerned, we can say that this space and time are the two factors that stem from the same origin, and the origin is space-time. So these are two different aspects of the same thing. The same thing is space-time, right? So this is like that. So this is a thought experiment of, you can say, the time dilation effect, and this is catching a ball on a rocket ship. This person throws a ball upward and this person catches it. So this is, and the distance between the two observers, or the distance traversed by the ball, is 4 meter. Okay, and the time taken by the ball to reach this person is 1 second, right? And the velocity of the ball is 4 meter per second. Okay, so it means that the ball took 1 second to reach this person from here to here. Okay, and so what earthbound observer observes? These observations these observations are the ones made by these inside observers. We are ground-based observers, and we are watching similar events. This is a rocket ship who is moving with certain velocity, and the velocity of the rocket ship is 3 meter per second. Okay, and so what we see is that this observer threw a ball at this location, and after a time of 1 second it reaches in here, but the ball traverses a distance of 5 meter, which is coming from Pythagorean theorem, which 3 meters square plus 4 meters square is 5 meter, and this is v naught t, and so this velocity is s over t, and so it means that the ball traversed a distance of 5 meter per second. In the previous case, it traversed a distance of 4 meter, if you remember. So this is 4 meter. So in this case, the ball took the same time, that is 1 second, but it traversed a distance more than the one observed by an inside observer, right? So location of the two events is different. Elapsed time is the same. As I told you, it's 1 second. The ball appears to travel faster because it traversed a distance of 5 meter in this case. So instead of a ball, we can consider a light flash. A light pulse or a light flash on a rocket ship. So this observer is having a torch or some sort of source of light, and he is throwing a light flash or a light pulse somehow, and this light pulse reaches in here. Okay, and this is the same distance. Okay, as far as the ground-based observer is concerned, the light pulse traversed an oblique path similar to the ball we observed, and this is the distance Vt, and so this is Vt square plus s square. So let's now make some simple calculations. This t is the time on Earth clock. Okay, this t is the time on Earth clock, whereas this t naught is the time on moving clock. Okay, this clock is inside the moving frame, and this is a clock lying outside of the frame. So as far as the velocity of light is concerned, then the total distance traversed, which is according to Pythagorean theorem, is Vt square plus s square over t, and this is the time of the moving clock, which is s, and this is over t naught. So this is more time, as we saw in the ball case. So this Ct becomes this, and this becomes this. So Ct squared is this, Vt square plus Ct naught square. And this equation can be reshaped as Ct squared minus Vt squared is equal to Ct naught squared, and this C square minus V square into T square is C square T naught square, and this T square is equal to C square over C square minus V square into T naught square, and this T square is 1 over 1 minus V square over C square into T naught square, and this T is equal to 1 over 1 minus V square over C square into T naught. So gamma factor appears here, and then we can put T is equal to 1 over 1 minus V square over C square into T naught. So T is equal to T naught gamma. So this is a simple mathematical proof of the time dilation effect. So as far as the graphical representation is concerned, as I told you, the time dilation increases as a function of increase in the relative velocity. So the more the relative velocity is, the more will be the dilation of time. Once we have a zero relative velocity, so the ratio will be 1, and we will have a 1 in here. So once we go up and up and up, so the time dilation effect starts approximately from here. That's 30% of the velocity of light, we can see, or even less than that. You can say some sort of deviation from here. So this is in fact a deviation from classical mechanics, and then it goes up. So with 50% of the velocity of light, you can see a clear deviation and increase in the time dilation effect, 60%, 70%, 80%, 90%. And this curve will never touch this vertical line. You remember, as I told you, nature has set an upper limit of the speed, and this curve will never land in here. So we can neither surpass this limit nor can reach this. So this is a graphical representation, and this is the tabular form. The values of gamma are summarized in here. When we have 0.01% of the velocity of light, then the value of gamma is 1.00005, and with 0.1% of the velocity of light, we have 1.005, and 50% of the velocity of light means we have gamma 1.15, and so for 0.99%, that is 99%, you can say that yes, 99%. So this is like, you can say 0.1%, this is 1%, this is 50%, 60%, 80%, 90%, and 99%. So this is in here we can say that practically with the advancement of technology we can go, you can say ideally, up to here. And because we cannot reach this limit, as I told you earlier, but theoretically this will give us the value of infinity of gamma. And again, an imaginary number, if we surpass this limit, then we will have a negative time. You can say that we will have a negative time. That is, we can go from present to the past. You can say that, which is impossible. And as far as the ratio of uh, velocity and velocity of light is concerned, and this is plotted with gamma, then gamma versus v by c will give us a plot like that. So this is the midpoint, which is c by 2, half of the velocity of light. And so the curve exactly adopts the same shape as we discussed in the previous slide. And so the Lorentz vector is in here. So this is basically a graphical representation of this table. And as I told you, this curve will never land on this vertical line. So relativistic increase in mass. When you speak of mass, you must specify whether you talk about relativistic mass or material mass. So this is inertial mass. Okay, this m is inertial mass, and this m naught is material mass in this equation. As far as the classical mechanics is concerned, Newton's school of thought says that these two masses are the same. You know, inertia is actually the resistance offered by a body once a force is applied on it to produce some sort of acceleration in it. So this is a reluctance, a resistance offered by an object, a material object. So this resistance and this material mass are actually the same in classical mechanics. But as far as the relativistic mechanics is concerned, then this m increases, this goes far beyond this m naught during high relativistic speeds, you can say that. And this increase happens by the virtue of this gamma. The more gamma we have, the more inertia of the body will arise. Okay, so hopefully you got that. As far as this inertial mass is concerned, upon velocity of light, it goes to infinity. That's why it's again impossible for an object to achieve the velocity of light. So a graphical representation, we have considered 100 kg astronaut, and this mass is increasing very rapidly, and this is becoming infinite as we approach c. So we can start from here. The mass is 100 kg, but this is the material mass because we don't have any velocity of light in here. So the material mass is of course 100 kg, but this is the inertia that goes up as we increase the relativistic velocity of the astronaut, and so it goes up in here. So once we reach, you can say 0.6 or 60% of the velocity of light, then the rate of increase becomes more and more rapid, and then it goes up rapidly. But again, because of the limit that nature has put in front of us, we can't surpass this limit, nor we can reach this. So this will, this will be separated. This will be having some sort of distance from this vertical line. This will never touch it. So Maxwell's equations are correct. We can say that. In the previous slides, we stated that either the velocity of light is relative, and if the velocity of light is relative, then Maxwell's equation would be wrong. But if the velocity of light in vacuum is absolute, then Maxwell's equations are correct. So we are now in position to clearly state that Maxwell's equations are correct. And this is the immediate implication, is that you can't even begin to catch up with a beam of light, no matter how hard you try. And so this is contrary to the intuition and common sense. So it's crazy, and the implications are radical. So the notion of space and time, I think I will discuss this notion of space and time in the coming video lecture, but you need to understand until here. So if you have any query, any confusion, any question, you can let me know on my WhatsApp number, or you can drop me an email to ask a question about this lecture. So I wish you good luck and all the best.